Hello, this is video 3A. I'm Mr. Miller and you're probably a calculus student. The title of this video is The Slope of a Tangent Line. Okay, well, in the picture here we have we see a tangent line and a secant line. Just to remind you, a tangent line at a point is a line that just barely touches the function at the point and it doesn't cross through the graph of the function, just touches it like here. A secant line is a line that intersects a curve in two or more points. And we're going to use secant lines to find the slope of the tangent line. The whole idea is the idea of the derivative. Okay, here we go. So let's start with a specific function. Here, we're going to use this function for a couple slides here as our main example. This function is the function f of x equals x squared minus 3. And we want to see if we can find the slope of the tangent line at x equals 3. That would be this point right here. This black point is the point on the curve that corresponds to x equals 3. The function's in blue here. It's a parabola. And the tangent line is drawn in red. And we want to find the slope of that tangent line. We're going to do it a couple different ways. The first way, I'm going to make use of some software I have to try to visualize it. So here we have the same function. This is f of x equals x squared minus 3. And this is the point we're interested in. In this picture, the graph is purple, the tangent line is red, and the one I can control is this blue secant line. So here, when I put the point B right here, it is way off. The slope of the blue line is very different than the slope of the red tangent line. But as I let this point B slide closer and closer and closer to C, we see that the secant line is getting closer and closer and closer to being just like the tangent line. And in fact, as I let B kind of continue and come really close to C, we can't tell the difference between the secant line and the tangent line. Okay, and here I'm going to put it right on top. And we see that the slope is 5.99, which is pretty much approximately 6. So the slope of the tangent line seems to be 6. So let's go back over here one more time. So right here I have the slope of the secant line. And this quantity right here, xb minus xc, that's actually delta x. It's negative because this point is to the left of the point we're focusing on. If I move point B so that's to the right, like over here, then we see that delta x is positive. So whether I'm coming from the right or from the left here, as I let B approach C, the slope of the secant line approaches the slope of the tangent line. Okay? There's delta x equals 0. Actually, the secant line is equal to the tangent line right there. So that's our strategy. To find the slope of a tangent line, that's kind of hard because we only have one point. We're going to use a limit of secant lines. Okay, well, we're going to come up with a general formula for this. Then we'll come back to that example and calculate it. All right, and show that it was 6. So here we have a function f is graphed in the blue curve. It's the same function in both graphs. And here we have a secant drawn. And we're interested in the tangent line at this point. So notice as we let this point slide closer and closer to the point we're interested in, these secant lines approach the tangent line. Okay, so their slopes are approaching the slope of the tangent line. So we need to put this in a formula somehow. So this is how we're going to do it. Going back to this diagram, this first point I circled is x, f of x. Okay? This coordinates of this point here would be this. The x coordinate is x plus delta x. We've added delta x to x to get a new point. And it'd be f of that. F of x plus delta x. Now, these are 2 points on the secant line. I want to find the slope between them, and I have the slope of the secant line. So the slope would be y2 minus y1 would be f of x plus delta x minus f of x. I just subtracted the y coordinates of the points. divided by the difference in the x coordinates. It'd be x plus delta x minus x. And that cancels just leaving delta x, which makes sense. Delta x is how much we change the x coordinates, and that's what we're left with there. Now, for the tangent line, we have to add something. We have to add the limit. The tangent line is the limit as this change in x goes to 0, as we let this point slide towards the point we're interested in. So the slope of the tangent line would be this. The limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. I simply added the limit to what we had here. The slope of the tangent line is the limit of the slopes of the secant lines. Okay, now, this is a big idea. It's the idea of the derivative. So notice the little f prime here. That means the first derivative, or the derivative of f. So the derivative of f at x is given by f prime of x, and it equals that limit expression we just wrote down. So if that limit exists, that's the derivative of the function at that point. Okay, and it gives us another function. All right, so if we take a derivative of a function, we get a new function. Okay, all right, well, let's try this. First, I'm going to kind of go back and forth. I'm going to find the derivative at a specific point, and that's a little bit easier. Then I'm going to go back and find a general formula for it. So here, calculation of a derivative at a specific point. We want to find the derivative of f of x equals x squared minus 3 at x equals 3. Well, we kind of already know the answer. This is the one I did the demonstration with. The answer is 6. But let's show how to use the limit to find it. So this is the limit. Delta x goes to 0. F of x plus delta x minus f of x over delta x. We're going to see a lot of this. Now, we're finding a specific point, so I can actually just put 3 in for x, and it makes things a little bit simpler, I think. So limit delta x approaches 0, f of 3 plus delta x minus f of 3 divided by delta x. Okay, so I'm going to keep writing the limit until I actually take it. This is the limit as delta x approaches 0. If I put 3 plus delta x into the function, it would be 3 plus delta x squared minus 3. I just substitute x plus delta x in for x squared, or actually in for x, minus, so maybe I'll put brackets around this, because that was all that first thing, minus f of 3, okay. If I put 3 in, I get 9 minus 3, which is 6, all divided by delta x. Now, we know there's a lot of algebra involved here, okay, so we can just kind of chew through the algebra. If I square this out, you would get 9 plus 6 delta x plus delta x squared minus 3 minus 6 divided by delta x. Well, the 9 and the minus 3 and the minus 6 cancel, so we have the limit as delta x goes to 0. I'm going to factor out the delta x here. We've been down this road before, so now this should be kind of looking familiar. We've done these limits. Delta x cancels, and we have the limit as delta x approaches 0 of 6 plus delta x, which is, well, delta x goes to 0. We're just left with 6, which we knew that was the answer. But here we did. We worked out the limit of the slopes of the secant lines. As the secant lines get closer to the tangent, their slopes get closer to 6. Wow. Now that's impressive. We're going to learn a lot of shortcuts, so we don't have to do limits for very long. All right, now I'm going to kind of go through the same process, but now I'm going to do it for any value of x. So, all right, so here we go. And this would be the derivative. So before I was finding the derivative at 3, this is the derivative at any value. So this is the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x, which is the limit delta x goes to 0 of, I have to put x plus delta x into the function, and this is squared, minus 3 minus f of x, which is x squared minus 3. So you gotta be careful to put parentheses around that, over delta x. This is really the same thing I was just doing. Instead of a 3 here, we have x because we're doing the formula in general. Okay, so we have a lot of algebra ahead of us. This is going to be ugly for a minute, then it's going to get short and sweet. So delta x goes to 0. We're going to multiply this out, so hopefully we're very familiar with that now. That's x squared plus 2x delta x plus delta x squared. We have this minus 3 minus x squared, and minus 3 is plus 3. So I'm going to cancel some things out. This x squared cancels, that one cancels, minus 3 plus 3, and I forgot, this is all over delta x. So here we are, we got to factor the delta x out, and we're actually getting close to the end here. So this would be delta x times 2x plus delta x all over delta x. That cancels, and as we let delta x go to 0, this is gone. The only thing that is left is 2x. So we get the formula that f prime of x is 2x. That's the formula for the slope of the tangent line anywhere. We were doing it at x equals 3, and if you plug in 3 for x, we get 2 times 3 is 6, which is exactly what we got. But this is a general form. If I want the slope of the tangent line at 0, I can just substitute 0 and get 2 times 0 equals 0. Okay, hang in there. We got 2 examples left. Alright, so here's another quadratic. And this one is an upside down parabola though. And we want to find the slope of the tangent line at 2. That would be the slope of this red line here. We're going to try to find that. Okay, well, let's do it from the definition. This is at a specific point, so I'm going to put in a value for x right away. So f prime, we're finding it at 2, is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. But like I said, we're finding it at 2, so I can put 2 in for x. And that makes the limit a little bit better. Actually, delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x. Okay, got time to plug into the function. So this is the limit as delta x goes to 0. I'm going to stick 2 plus delta x in there. So this would be 5 minus parentheses 2 plus delta x squared. All of that, that's the first thing here, minus f of 2. If we substitute 2, 5 minus 2 squared is 5 minus 4, which is 1. So I'm just going to write minus 1 all over delta x. We know this is going to be painful for a second. So this is a limit. Delta x goes to 0 of 5 minus, here we go, 2 squared is 4, plus 4 delta x plus delta x squared. That's what we get when we square this out. Minus 1 all over delta x. I'm running out of room here, so I'm going to kind of do some quick simplification. So this is the limit as delta x goes to 0. Alright, this 5 cancels the minus 4 and the minus 1 there. And I'm left with I'm going to factor out delta x. Delta x times. I have a minus 4 delta x. That's just minus 4 when I factor out the delta x. And I have a minus delta x. So I have minus 4 delta x minus delta x squared. I just factored out a delta x over a delta x. And, sorry about that. And those cancel. And as delta x goes to 0, I'm only going to be left with this minus 4. So this whole thing is minus 4. That's the slope of this line here. For that line, m equals negative 4. And that's the derivative at 2. Okay. Now, guys, this has been a big workout here. So our last step is we're going to go back to the same function and calculate the general formula for the derivative. Okay. And we're going to practice this a lot in class on our own. So f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, which equals limit as delta x goes to 0. Whew, we got to put 5 minus x plus delta x into 5 minus x squared. So here it is. 5 minus x plus delta x squared minus f of x, which is 5 minus x squared. So this is where the algebra skills kick in. So here we go. Equals the limit as delta x approaches 0. I'm going to square this first before we do anything. So it'd be 5 minus x squared plus 2x delta x plus delta x squared minus 5 minus x squared all over delta x. Man, this is awesome. Okay, well, we got a lot of things to cancel. So this equals the limit as delta x goes to 0. Alright, hopefully I have enough space. I'm going to distribute the negative. So I'm showing all my work. 5 minus x squared minus 2x delta x minus delta x squared minus 5 plus x squared all over delta x. So let's see what cancels. I kind of multiplied everything out. 5 minus 5 cancels. The minus x squared and plus x squared cancels. And I'm going to factor out a delta x and what remains. So this is the limit as delta x approaches 0 of delta x times minus 2x minus delta x all over delta x. Those cancel, and I'm left with the limit as delta x goes to 0 of minus 2x minus delta x. Wow. And as delta x goes to 0, that's gone. It's just minus 2x. Holy cow. Now, at x equals 2, on the last slide, we got negative 4. And you can see that works. When we put in 2, negative 2 times 2 is negative 4. So here's our general for the formula for the slope of the tangent line. F prime of x equals negative 2x. So if I put in x equals 0, negative 2 times 0 is 0, and that gives me the slope of the tangent line here. And that makes sense because the tangent line's horizontal. If I put in x equals 1, the slope is negative 2. And x equals 1 is right here. And that makes sense because the tangent line's kind of going down. And if I put in negative 2 times negative 2 is 4. And that makes sense also because that would be the slope of this tangent line. So now I have a formula for the slope of the tangent line anywhere on the curve. Wow. Now, this is incredible, but it's going to get really short soon. We're going to find shortcuts for derivatives. First, we have to put on our algebra muscle and use limits, but then we're going to use some rules for finding derivatives. Okay, I have a one problem for you for the journal assignment. This one's going to be easier because it doesn't have an x squared in it. So I want you to find the derivative, which is evaluating this limit for this function here. F of x equals 3x plus 2. Like I said, the algebra is a little bit better because we don't have to square anything. All right, show all your work, and we'll take a look at it in class. Take care.